into area, and this that is the change in the pressure due to the length of the fluid. So here you may see that is the both pressure always acting inwards of the system. So sum of the forces acting along that is our S, where it is the mark, the coordinate system del Z, that is the. So P into dA along the streamline opposite to the streamline minus P plus del Py del S into ds into dA. So see here that is the some, that is the, you might be confusing, that is the coordinate system length. Actually the P plus del Py del Z into dz is not correct. This one that is the actually correct, del Py del S into ds, due to the length of the fluid element is ds into area, and the our weight that is the rho g dA ds. So here it is the inclined, the streamline that is to the horizontal is theta, it is mentioned in the figure with respect to that is the horizontal line, and v velocity stream that is along the streamline. So rho g sine theta into dA into ds, and sine theta is nothing, that is the dz by ds. So summation of forces along the streamline equal to the minus del Py del S ds minus rho g dz into d. So we now that is the consider a velocity of a point, or that is the of the in the fluid or fluid particles. Here it is the positions are marked, that is the r and r plus dr at a time t. After that it is t plus del t. Then from the total derivative what we have discussed, that is the local plus convective, that is the written here del vy del t u plus del vy del x v del vy del y. This u v are the velocity component x y direction, and the velocity along the streamline, that is the curve that is the given. So tangent to that line give del vy dt is the del vy del t local plus convective. So in this that is the second. So rho into dA into ds. So here minus del Py the del S into ds rho g dz into d. So this is the rho into dA into dc. This is the mass. Mass into the acceleration is the sum, that is the mass into acceleration. So rho into volume, that will come out, that is the mass into the acceleration, which is written del v by del t plus v del v equal to the sum of the forces. And this is the generalized form of the Euler results. On a steady form, you may cancel out some terms that will come out. Is it correct? So here, this convective term v into del v by the del s, or we can write it del y del s into v square y2. Then this, that is the equations written in after the integration for the 2 points. Rho del v square by del t into ds plus rho v1 v2 square minus v1 by 2 plus p2 by p1 minus rho g z1. And this is the unsteady form of the Bernoulli equations for two sections 1 and so this is the very important. Generally in the books, all these are written for the steady state and specific conditions. Here it is written for the unsteady state. When we will write down the steady state, then that will become that is the P y rho b square by 2 plus rho that is the gz constant is the static P is the static pressure is the rho into v square by 2 is kinetic or dynamic is z potential energy. Same equations you may also derive by the some other form. This is the second method is written. Ultimately you should also get here. Just wait. So here that is the velocity equal to the that is the give your here the equations v dv ds equal to the minus 1 by rho dp by ds minus g dz by ds. And this is the above equation also that is the here del v by del t plus v del v by ds minus 1 by rho del p by del s into g dj ds. This is the Euler equations in the term of again that is the unsteady, and when we should take the steady equation we cancel out the local velocity change with the time and equation for the one dimensional non-viscous inviscid that is the and integrate that equations again it will come out v square by 2 plus p by rho gz is constant, or you can say that is the v square by 2g plus p by rho g plus z equal to the constant, and rho v square by 2 plus p plus g rho gz is constant. See, all these are the equations for the Bernoulli equations. So see here, rho v square by 2 plus p. P is the pressure and pressure is the here written. So see, that is the unit rho g z. So you have to check first one 3.5 or simply 3.6, you can check it. 3.6 Bernoulli equations are written in the term of the head. Every term that is the Z potential head you may see B that is the in the term of the head. 3.7 C that is the in pressure. Rho G Z that is the written in the potential energy form. So either you can write the Bernoulli equations in the term of the head or in the term of that is the energy. Generally, the civil people use the head form and the other engineers maybe use that is the energy form. But we have to also discuss the head form for the flow through the pipe. So here that is the written V square by the 2g is the velocity head, Py the rho g is pressure head, Z is the potential head, summation of these is the total. So this is the your Bernoulli equations. So Bernoulli, as you might have seen from the Euler equations, we have chosen that is the inviscid, no friction. Otherwise, viscosity will play the role. So inviscid, then a steady, incompressible, and along a streamline. Here that is the situation is written for the steady state, but you might be aware and also know the unsteady state situations. It is not always the steady state. But these equations right now which I have shown you in the steady state. Some useful things to be the required for the Bernoulli equations. So see, use the continuity first to reduce the number of unknowns. See, when we are going to apply the Bernoulli equations, then you may also aware because it is the incompressible. So our continuity equation will become del u by the del x plus del v by the del y plus del w by del z equal to 0 if it is a three-dimensional and a steady state. Then you should get the this. Or dimension is reduced form or is reducing then you may write to accordingly two dimension one dimension. So first we, we will apply the continuity, maybe reduce the unknowns. We can see all these things in the examples. Free surface, that is the when we are assuming free surface flow means atmospheric pressure. For a free discharge to atmosphere is also pressure should be atmospheric. In case of the large tank and reservoir, velocity at the surface is unaffected by the discharge. So if the streamline is horizontal, then the term that is the rho gh is omitted because at the same level both at the same head. So that is not play any role. And rho v square y, that is the dynamic pressure, and P, that is the static pressure, and PT is the total pressure. Sometimes or generally in the thermodynamics or in the higher, this term is treated as a stagnant pressure. When we should study the pitot tube, this equation will be used. Application of the Bernoulli theorem. When we have to study the pitot tube. Then, so see, summation of the dynamic pressure and static pressure is total pressure, and it is also called a stagnant pressure. Treat with fluid that is stagnant. When it will come in contact with any measuring devices, then it is still a stagnant. Here, that is the see a figure flow through that is the converging system. A1 is the larger area and A2 is the smaller area. So here pressure head plus kinetic head, because the streamline in the same head, streamline is not changed. Only area, so at the same head, that's why Z1, Z2, both that is that from the streamline that is the same. So that is the not added here. So pressure head and that is the velocity head is compared. From the continuity, we can write at the two section, it is the one dimensional situations for the incompressible flow. Always remember the Bernoulli equation is written for the incompressible, so obviously this is also a play role. So when area is greater than velocity is less than, from the continuity we can say that. And if it is satisfied by the continuity equations, then from Bernoulli equation we can say pressure at the section 1 is greater than at 2. See, area is larger, velocity is lesser, pressure is larger. These things we have to justify in experiment number 2, Bernoulli experiment. where we can see how it is the pressure is, that is the fluid will be rise in the tube according to the converging diverging system. These things we have summation of the pressure head, dynamic head, and potential head remains constant. We can check from the experiment. And here again I am telling from the continuity area is larger, velocity is smaller. From the Bernoulli, velocity is a smaller, pressure is large. So that's why we are applying the system the one to another. So that's why these both equations are twin. That helps you. See the figure 3.5. This is the generalized figure. Section, that is the cross section of the flow is mentioned here is the two types. At section 1 area is A1, at section 2 area is A2, at section 3 A3, and potential head, that is the elevation is given Z1, Z2, Z3, and from we are taking the elevation is called datum. Here see, then from the water tank from 1 to 2 passing through the different, that is the cross section pipe. Then at section 1 pressure head P1 Y rho G, and kind, that is the dynamic head velocity head V1 Y the rho G. Similarly at that is the point section 2 क्या पढ़ी?
प्रोसेस का रजिस्ट्रेशन ऑनलाइन जैसे हम लोग बीटेक हम लोग खुद करते हैं स्टूडेंट्स का, तो इसमें क्या है ये
लोग नोट कर दिया, हम करेंगे तो फिर बहुत निकालेंगे, फिर उसे कलेक्ट कर लीजिएगा ऑफिस से।
तो ये अभी एड सबसे साइड।
हाँ हाँ। So see, that is the interesting thing is that at section 1 is 3 terms. Z1, P1 by rho G, V1 square by the 2G. Simply, that's all. At the section 2, in addition to the Z2, P2 by rho G plus V2 square by 2G, one more term is here added, that is the H2. At section 3, Z3 P3 by rho G plus V3 square by 2G plus H3. So see, in the initial things, that is that the inlet through the any channel, through the pipe, any section, there is a starting no loss. After that it may be the chance of the losses, head losses. So that's why here it is the written this equation. See, Bernoulli equations we have written at section 1, section 2 and section 3. At section 1 simply 3 terms. Summation of all energy means kinetic, pressure and potential, that is the concept. At the section 2 is it is added H2 and H3, that is the head loss or losses due to the friction, which we will discuss in the losses. So but at the starting section there is no any loss because it start to flow, and after that it may create some losses. That's why it is always losses is added to the other than first section. So in that is this here, the line connecting the height of the pressure head at respective point of the pipeline is called hydraulic grade line. See the connecting the height of the pressure head at the see the dotted line here. See, dotted line is marked, and that line is called hydraulic grade line. Above that, that is the velocity head, and then it is the losses, pipe losses. See, you must mark that is the check it. So that is the pipe line. So the line connecting the height of the pressure heads, connecting the height of the pressure head Py rho g at respective points of the pipeline is called hydraulic grade line, while the connecting the height of the heads means pressure head, velocity head, and potential head is called energy line, is called the energy line. See, so hydraulic grade line is only called pressure head or pressure that is the head, and total head, potential head, pressure head, velocity head is called energy line. Then this is the your Bernoulli principles and head. Am I right? This is the Bernoulli principles, Euler principles, and head. Then come on, that is the applications of the Bernoulli. Are you listening or not listening?
Yes, sir, listening.
Okay. Applications, that is the here applications of the Bernoulli equations. First, that is the pitot tube. This is your pitot tube. Point A at the mainstream line. B is away from there. See, and at the A and B, where that is the pitot point, that is the contact with the water. C is a cut, and C is the any that is the flow, and A is passing through our measuring devices. So both these are the connected to a manometer or head difference, which is marked by the edge. So see, pitot tube is a device where the lower end of a glass tube is bent by 90 degrees. This is the glass tube bent by the 90 degree. That is the HH, that is that tube system. And supported against the flow. The flow velocity is to be measured by measuring the increased height of the water level as shown in the figure. This is actually nothing but that is the difference of the level. One with the center, another one for the free stream. So the tube is so designed that at the streamlining the hole is open in face of the flow, while another in the direction vertical to the flow is used in order to pick out the separate pressure. So C at the free stream flow and B at the stagnant, that is the at entering that through the system. So let P, A and VA respectively the static pressure because the fluid come in contact with, that is the B A, that's why it is called a static. So velocity at position A of the undisturbed upstream flow, and at point B of the pitot tube the flow is stopped. So it is stopped. So flow A making the velocity 0 and pressure PV. So B is called a stagnant point because it is a come in contact with the our system which is a stationary, and A, that is the coming with some velocity towards the point B. So apply the Bernoulli equations between point A and B. So because that is the C, here the both are in the same streamline, AB in the same line. So potential head remains same. So we have eliminated, and pressure at any, that is the point A, PA by rho G plus VA by 2G equal to the pressure, because it is a stagnant, it is a not moving, it is a contact with the solid things. So velocity is pressure difference root under by rho. So in a parallel flow, the static pressure PA is same on the streamline adjacent to A and detected by the whole C, normal to the flow. So A is also this, and PB minus PB minus PC by rho G and VA equal to the root under 2GS. In case where the flowing fluid is a gas, PB and PC is measured with the U tube. However, with actual pitot tube seam, some loss occur due to its shape. So the velocity VA, that is the flowing fluid velocity VA is equal to the root under 2GH. H is nothing pressure difference in term of the head, and CB is coefficient of velocity. That actual velocity is lower than the root under 2GH, which is the measured by the pitot tube. So that's why it is multiplied by the sum coefficient of velocity. And this pitot tube is also available in our lab in a model form. Next, that is the Venturi meter. Venturi meter is available in our lab in model form, and it is attached to the Francis turbine, Kaplan turbine, and Pelton turbine. All these turbines are available in the fluid machinery lab, and this is the also model is available. So see, what is the Venturi meter? First see, Venturi meter is a device to measure flow rate in a pipeline. So Venturi meter is a device to measure the flow rate discharge in a pipe. It consists of two conical parts with short that is a small section portion of uniform section is called throat in between. So see, there are three components of the Venturi meter, or three parts of the Venturi meter. So see, the starting, that is the tube, is converging type. It is, that is the first part is converging. Then it is the uniform area, that is called throat, and which we go to the exit outside or connected to the another, that is the other part of the pipe, is diffuse, diverging. So it is called converging cone, that is a converging zone, diverging zone, and throat. So all these are the three portions. So in that is the course of the flow through the converging part, means first part always connected inside, that is the converging, and exiting, that is the second part with the diverging. Velocity increases in direction of flow because the area decreases. According to the principle of continuity, cross-sectional area decreases. So the pressure decreases according to the Bernoulli equations, and reaches a minimum at the throat uniform cross section. So decreases, say, then velocity increases, and then pressure decreases, and then it reach to the minimum, that is throat force. So the flow rate is measured by measuring the pressure differential across the converging cone using a manometer. So say the pressure difference we will measure between the throat and converging force. And it is the built up in that is the machine or in manometer design where to connect the converging force. It is the then question arise, what is the role of that is the diverging force. So subsequent to the throat and increase the pressure and decrease in velocity take place in divergent section. Hence the function of different parts of the Venturi meter is like that. Converging cone accelerate the flow, throat high velocity and maintain it for a short length, diffuser to restore the pressure as nearly as possible to the original. Means the entering pressure it is maintained. So this is the equations written for the Bernoulli equation, point 1 in the converging section, point 2 at the throat, and converging angle is 20 degree, diverging angle is 6 degree, angle is lesser, so length is larger, and not create the suction pressure. That's why we use to take the larger length of the diverging section. So see here both are the written, rho g is the gamma. So this is the written here, Bernoulli principle, section 1, 2, section 1 is the converging, section 2 is the throat, and rearrange, and finally the find out the velocity at the throat is written here. And now apply the principle of manometer at section AB. So here, that is the mark, that is the section, the line AB in the manometer. So that line represents, that is the equal pressure. So see, at the left end, limb is A mark. So that is the P1 plus Z1 minus H. Here P1 is the pressure at the point 1 plus Z1 plus, that is the, here the mark, that is the height H, a small h, which is shown here below from the datum line to the reference line AB. A is H. So that is the P1 plus Z1 minus H into rho G. Right side limb at the B. This is the at the B. So del H is the manometric fluid height greater than the A, whose density is the rho m. So P2 pressure at the throat, Z2 minus H minus del H rho G. So see Z2. Z2 is the elevation from the datum to the point 2 minus this H1, datum to the height A, B level plus it is at above del H into rho G plus del H into rho m into G acting in the right side. So plus del H into rho m, that is the manometric fluid density into G. And this will give you V2, and from V2 we can find out the discharge Q. Always remember, this is a not actual discharge. Some losses also takes place. So that's why it is a written theoretical discharge. A2 into V2. When we will study the coefficient of discharge, coefficient of velocity, and coefficient of contraction, then we will again discuss theoretical discharge, actual discharge, all these things. So say here, that is the, we got the velocity in the term of the pressure, area, and Z. That will transform pressure in the manometric form del H rho m by rho minus, because the our Venturi meter is connected with the manometer. Then you can read the del H easily, and densities are known of the manometer, and measuring fluid discharge is also known. In that is the turbine, generally we will use the manometric fluid is mercury and measuring fluid is water. So from the equation number A2, that is the discharge velocity. So A, that is the A1, A2 cross section area at point 1 means in the converging section, and at the throat. Both are the known. Converging cross section area is nothing but the dia, that is the cross section area of the pipe to which we are interested to find out the discharge. And A2, that is the minimum area, that is the throat area. So diameter you can measure or it is immense. Del H difference in the manometer height and density of the both fluid. All these are the new known. Then you can find out the discharge. And such type of the discharge is not actual, but it is the theoretical. Actual discharge is some lesser than the theoretical discharge. Third, that is the equipment orifice meter. So see, this is simple and cheap. So an orifice meter is essentially a thin circular plate with a sharp edge, concentric circular hole in it. The orifice plate creates an obstruction. See the obstruction area, that is the obstructed is H is, that is the mark A naught. So obstruction to the flow by the providing flow with an area A naught, much smaller than cross-sectional area of the pipe A1. So this is the A naught, that is the our smallest area or obstruction. So the flow past the orifice contracts the extent the section sees. See the line. Not at the minimum area, just after that. And so called the section of formation of vena contract. This is the vena contract area is, that is the slightly, that is the given beyond the A naught. And this is also a relations between the vena contract area and minimum and given area. All these have some relations. So the flow past the orifice contracts to the extent a section CC, called section of formation of vena contract. Then applying the Bernoulli equations at section 1 where area is pipe or which we have connected the resource, the either maybe that is the tank, maybe the pipe, and at that is the vena contract area line CC. Interesting thing is that is CC and manometer is connected here, and manometer difference between the 2 points or two sections at one, that is the connected to the pipe dia, or another one at vena contract, not exactly at the smallest area point. So difference is given del H. So that will similar, that is the what we did, just only here area is marked instead of the 2 is nothing but the vena contract area with the subsuffix C. So see, so velocity, that is the here. So see previous equations. V2, that is the here written is A1y root under A1 square minus A2 square. Take the inside, then it will become 1 root under 1y root under 1 minus A2 by A1 square. And A2 is nothing but the vena contract area. Sorry. So the and rest 2g del h rho m by rho minus 1. So 2g del h rho m minus by rho. and this is the difference is here in the manometer level. So the actual velocity is, however, less than the theoretical, and this is the velocity at the vena contract, which is the theoretical, and subsuffix is c and theoretical. Always remember, this is the all the velocity we got from the relations is theoretical, not actual, and this is the in previous case or in that is the here we have used that is the Venturi meter at point 2 means at throat. So velocity 2, but here at the vena contract, not at the V naught. So the an account of the friction. So V actual, see, V actual divided by the V theoretical is called coefficient of velocity. V actual, why the V theoretical is nothing, coefficient of velocity, and all these coefficients are less than 1. So actual velocity at vena contract point C equal to the theoretical velocity at point C into CV. So again, from the continuity equations, discharge equal to the area into velocity at vena contract section or point C. And here, an AC by the A naught into A naught equal to the VC actual. Is it visible or not visible? Hello? Is
Yes,
it
sir,
visible?
visual.
Visual.
See, try to understand here. See, please see. From the continuity equations, discharge that is the area, vena contract area, vena contract velocity actual. So when a contract area divided by the area at the minimum O into A, that gives same into velocity at vena contract actual. So AC, area at the vena contract divided by the area at the lowest point A naught. This is the A naught, see, this is the A naught, is called CC, coefficient of contraction. Coefficient of contraction into area at the minimum point cross section into velocity at vena contract actual. So coefficient of contraction is nothing, area at contraction point divided by minimum area, and that is the, so since AC cannot be measured directly, it depends on the flow and system, maybe how much that is away from A node. Hence, the discharge equal to the AC VC actual equal to the coefficient of velocity into coefficient of the contraction into the minimum area of the orifice meter. It is known or given into 1 y root under 1 minus a naught square cc square y a1 square. A1 is the area of the pipe. It is also given, or you have to easy to measure. And root under 2gh rho m by rho minus h. So see, here all relation is coming. And this coefficient of velocity into coefficient of contraction is nothing but it is the coefficient of discharge. this is also we got a relation. See, first I have discussed coefficient of velocity, actual velocity divided by the theoretical velocity, then coefficient of contraction, that is the area at contraction divided by the minimum area, A naught. So, and the product of coefficient of discharge is nothing actual discharge by the theoretical discharge. Or we can know the all these relations. Here we can, so if CD is CC, so Q that will become here all these constant, and the ratio of the orifice to pipe area and Reynolds number of flow. So inherent C is the fact that downstream manometer connection is the vena contract. However, if that change value of C which is, so these are the some coefficient of velocity, coefficient of contraction, coefficient of that is the discharge, all these. So let us see just quickly. So coefficient of velocity is the nothing but the ratio of actual velocity of the jet at vena contract to the theoretical velocity of jet, and given y the CV is equal to the V root under 2GH, which we got it from the relations at the theoretical velocity. And CV, this is the important. You must know about the roughly these data, not exactly, but roughly you must remember. That will help you in the numerical problem, sometimes not mention and in Viva voce. So CV varies from 0.95 to 0.99. Always remember, in the competition or in the exam, may be confused. But simple thing, CV is maximum, approximately 100%. So CV varies from 0.95 to 0.99, and it is valid for the rounder fish or square edge. In the competition, that is sometimes it is a mark for the round edge or for that is something other. But in the round, it is the highest. The actual discharge through orifice is the product of actual velocity at the vena contract and area of the jet at the vena contract. So Q equal to the ACCV root under the, and AC is the area of the jet at vena contract. Coefficient of contraction. So area, so it is a defined ratio area of the jet at vena contract to the area of orifice, and is given by AC, area at the vena contract, and area of the pipe or orifice because it is connected to that one. And coefficient of contraction is 0.61 to 0.6. It depending on shape and size of orifice and height of the liquid. So generally it is the 0.6 valid, 0.6 that is to the 0.7 highest, that then last that is the coefficient of discharge is actual discharge from the orifice to the theoretical discharge from orifice. Or you can say that that will relate actual velocity of jet into the area of the jet at vena contract, so it's minus contractile. So theoretical velocity gonna area of the, or that will come out coefficient of discharge equal to the coefficient of velocity into coefficient of contraction. See, coefficient of discharge is product of the two decimal points. So it is always less. So lowest is the coefficient of discharge, highest is coefficient of velocity, and coefficient is contraction is lies in these two things. However, it is always limited, but coefficient of discharge out of these is minimum, coefficient of velocity is maximum. Sometimes coefficient of contraction and coefficient of discharge may be minutely different, but still it is a product. Coefficient of discharge is product of the two decimal, it will always give lowest. You must take in the examination competition, you may confuse, just you should remember coefficient of velocity is highest, coefficient of discharge is product of the two things, so that's why it is given lowest. That's all. So this is the 0.6 to 0.65, 0.61 to the 0.69. These range are the same, but when you have to differentiate all these things, you must apply your common sense, then you can differentiate. In the examination, sometimes coefficient of velocity, contraction or discharge may be given, not given, then you should take always from the roughly data, but not take the absurd data. 0.95 to 0.99, you should not take point that is the 65 for the coefficient of velocity. And coefficient of that is the discharge, it is hardly 0.6 to 0.65 or otherwise mentioned in the question paper, or you should not take 0.99. These are the absurd data. So these are the some outlines, some that is the our idea about the fluid dynamics, and we should continue this thing in the next class. If you have any query, then ask me. If you have any query, is it interesting or not interesting? What do you feel? What is your feeling? Just tell me. Are you reading or not reading the book? Just tell me.
Yes, sir, reading.
Yes, please take that is a follow that is the same times you go through the book. I will send the in the next class after completing the theory, then we will take the examples. Okay, thank you.
Thank
Thank
you,
you,
sir.
sir.